Hello, everyone. Could you hear me? Okay. Yeah, thank you. First off, um, you you probably noticed the email I sent out yesterday um, about BondLab. There was an accident. I was trying to check my Blanca folder, and I try to remove some of them. And then accidentally, I removed our BondLab folder, so everything is just lost. Um, but no worries. If you choose to work on the older bonds, which would not show the score in the scoreboard, but feel free to work on the older bonds, and then we can grade manually. Basically, you send me an email and saying you want to grade, and then we can start a team call, and you just show me how you prevent explosion, and what is your answer keys for each bond, and uh, um, and then that's it. We can manually grade it, or uh, if you want to use the scoreboard from I believe the noon yesterday, you can apply a new bomb. The system is still running, but it only impact the older bombs before yesterday noon. Okay. Is there any questions about a bomb lab? A question from John Michael. If we had finished an older bomb, was that saved in the system before? Um, so it is not. It was saved in my bomb directory. Everyone's bomb was in that because I accidentally delete all my home folders basically. Um, so we didn't keep a record of the older bomb, but you can still show me your bomb, and then um, show me the answer keys. Um, that still works. Any other questions? Okay. And I learned from the experience. Um, right now, I set up a folder called a trash um, in my home folder. So I tell myself, don't use RM again. Use MV, move the folder to the trash, basically simulate the trash stuff. So if I accidentally delete something, I can still find that in my trash. So hopefully I won't have such a issue. Um, and okay, so the next one is um, for our today's class. We will first go through the homework two. Yeah, thank you for the suggestion. Today I will go through the homework two and how to solve each functions and give you the answer keys. Um, and after that, we will continue to do one exercise or two. And this time we are doing pop quiz. If you open the canvas, you will find um, under the assignment, I will show you later, there is a pop quiz number two. That is where you can submit your answer keys. Okay, let's first look at homework two. Okay, homework two, we are having four functions. we are trying to do reverse engineering. And for the function one, sorry, okay. For the function one, the function looks like this. You may notice there's if def, that is for me to generate who am I.c with answer keys and without answer keys. So you can just ignore it. You don't have to put the macro here. So the function one, if you look at it, it is about doing arithmetic calculation. And I just take the screenshot of the core assembly language that is trying to do that. And to solve this func1, to do the reverse engineering, let's look at how we can do it. First of all, at the very beginning, you may notice we move EDI to the EBX and the ESI to EBP. The reason to do that is because next we are trying to do a printf, and we need the EDI. So we wanna keep the value A intact. So we first move EDI to EBX. So the EBX would have A inside, and the ESI, which receives the second parameter, and would be moved to the EBP. So EBP would be B. And if we look at the LEA part, that is part we're trying to do the calculation. RBX, that is A. RBX to A. EAX is where we store the value. So we would have the AX equals to 2 plus A plus A times 3A plus 2 for the EAX here. First EAX. And then the next LEA, we would find the RAX is do the EAX. RBP, we talk about RBP is EBP, which is B. So we would do the EAX again, is number 2. And this time we are having RAX at first. So we have 3 times A plus 2. And then we plus B times 4. This will be the result for the EAX afterwards. The third one, we would have the EAX to be the EBX. EBX we talked about, that is A times the EAX, which will be 3A plus 2 plus 4 times B. So we find the EAX is this expression, and we talk about the EAX is a register to store return value. So we just return this calculation. This is the way we can solve this reverse engineering for func1. Any questions? Okay, good. This is the second function. We can do the reverse engineering. For the second function, if we look at the assembly, we're testing EBX. Again, from the previous part, the EBX is having A EBX is having A, and EBP is having B. For the same reason, EBX right now having A and EBP have a B. We are trying to do a test over A with itself. If it is less than or equal to, we will jump to offset 33. So we can find out the branching point right here. If A if A is less than or equal to 0, we would go to plus 33. Otherwise, we would stay, which would be A bigger than 0. We would stay at the current assembly. Okay. And if we stay at the current assembly, the next step we will do is we have the variable B shift to the right by one place. This is what we do if we stay. And then afterwards, we would subtract 4 out of EBX. Again, EBX is A, so we would have A minus equal to 4. And then we still do a test, EBX. If greater than, we would jump back to the, here is greater than, we would jump back to the 24. So here we do a test. If A bigger than 0, then we should jump back to here, right? And we just finished this branch. Let's look at if A is smaller or equal to 0, what would happen? We go to number 33, and we would move EBP to EAX. We talked about EAX is where we return values. We would return EBP, which is B. So if we, by looking at this assembly, you can draw the flow of this assembly, and you can come up to find that this is a looping, even though at the beginning it looked like a branching, but afterwards you find if A bigger than 0, you would jump back. So it's actually looping. So you can find the looping condition, A bigger than 0, and inside of the loop, we're doing a shift, and then -4 from A, and after everything, we would return the value B. So this would be the reverse engineering solutions. For this Funk 2, any questions?
I have a quick question.
Yeah, go ahead.
When I did the A equals A minus 4, I initially started with A minus equals 4, and I got really weird output. At the assembly level, is A equals A minus 4, is that the same as minus equals, or is there something that's different on like the back end for C?
I believe it should be the same, but you know, it's a compiler sometimes may deal differently with the two forms. But yeah, no worries. As long as you put down A minus equal to 4 or A equals to A minus 4, I think that works as well.
Did that happen for anyone else?
Sorry, could you say again?
I was just asking the class if that happened for anyone else. I was just curious about that.
I see.
Oh, well, it was probably just a typo on my behalf then.
Okay, yeah, no problem. Yeah, sometimes it looks like the C code look like the same. Sometimes the compiler may behave differently, um, but in a sense, it be shouldn't be have no problem. Um, so okay, yeah, that's a good one. Any other questions? Okay. Oh, maybe if you compile the code, maybe the optimization level could be another factor. Choosing different optimization levels, the compiler will give you slightly different codes. Okay, let's look at the function 3. For the function 3, let's read through the assembly. So at the very beginning, we still have the EBX to be A, there's A, and the EBP to be B. So at the very beginning, we're testing whether A equals to, we're testing whether A is bigger than 0 or less than. So if we find A is smaller or equal to 0, then we would jump to 39. If not, we would stay at a current flow. And if we stay, the next step we would compare EBP, which is B, and find out whether B is bigger than 4. If B is bigger than 4, then the next one, set G, this is a conditional set, would be satisfied. We would set AL to be 1. If B is smaller or equal to 4, and then in this case, we would set the AL to be 0, right? And let's look at the next step. Move ZBL basically would set the remaining part to be 0. When we move AL to the bigger space EAX, we would set the empty space to be 0. And then we would do a LEA for the LEA part. So we would do that all together. Oh, sorry, this way. For the LEA part, if you do the calculation right here, you would find we're trying to look at RAX plus RAX times 1, and we have offset minus 1. So if you do that, you will find we're doing 2 times RAX minus 1. And in our left case, if AL equals to 1, the result would have RAX equals to 2 times 1 minus 1, which will be 1. And then here, if AL equals to 0, and you would find that RAX would be 2 times 0 minus 1, which would be minus 1. In short, this LEA part is trying to make a number to be 1 and the other one to be -1. This is the trick to use. Set G only set AL to be 1, 0, and we wanted the number is not 1, 0, but 1 minus 1, and then this is the way to do it: 2 times the number minus 1. And after it, we make the jump to some other places. We'll skip the next move. So you can see here, if we stay, if a bigger than zero, we would have such a logic in the C. If we go the other direction, if a is smaller or equal to 0, we go to 39, and for 39, we move the all ones to EAX. That means we return -1. -1 in the 2's complement encoding, that will be having all ones to denote -1. And if we look at the C program, it tells us exactly the same thing. If a bigger than 0, we go into internal logic. We're trying to find out if a is bigger, if b is smaller than 5, and then we should return -1. Otherwise, we should return 1. And if a is smaller or equal to 0, and we return -1 directly. Okay, this is the answer key for function 3. Any questions? Okay, for the looping or branching, I would suggest you to draw a roadmap like this to clear out what is a flow of this program, and then you just write a C program, no matter it's a while loop, for loop, or branching if else, and then you can write down directly. Okay, if you don't have questions, let's look at Func 4. For the Func 4, you may notice at the beginning there's a get char that is trying to read from the input a character. And here is get char. We get the results. The results is in the EAX, because EAX always carry the return value. This will be your input. And we use the EAX. First of all, do a bitwise AND. So here is a bitwise AND. And we're trying to look at this bitwise AND whether equals to 3, 4. If it is equals to 3, 4, we would set the AL to be 1. That means we use a conditional set. If they are equal, and then AL should be 1. Otherwise, AL should be 0. And move ZBL is just try to make the EAX to be the number. Okay. And if we look at the C program, it will look like this. And for the so this will be the reverse engineering for Func 4. And we have 2 questions. The first question is, what is the return value for Func 1, Func 2, and Func 3? And for this question, you can run the quick way is you can use the GDB. When the Func 1 is about to return, you just check what is the value of the EAX. And then the whatever value in the EAX would be the return value. You can do the same thing for func2 and func3. Just to check the EAX value before this function is about to return. This is one way you can check the return value. The other one is because you already figure out the, if you already figure out the C program, and then you can look at whoami.c, you can find out if we give the input A equals to 10, B equals to 20, and then you should figure out return value using the C program as well. So these two methods, they are able to find out the return value. And the second question is, what should be the character we give to make func4 to return 1? Here I will give you my solution. If we want to give an input character making func4 return 1, that means this character, when do a bitwise AND, the value should be 3, 4. If we put down the number right here, F5, it will be 1, 1, 1, 1. This is a binary. 5 is 0, 1, 0, 1. Okay, this is F5. We need to find something here. This is our character that make the result to be 3, 4. If we look at 3, 4, 0, 1, 1, this is 3. We look at 4. Okay, this is a 4. Now let's look at how to make that number to be to satisfy this equation, because at the rightmost digit we have 0 as a result, so we know that the rightmost digit of this character should be 0. And next one we have 0, 0. So here we can have any digit, no matter it's 0 or 1. We would have 0 in the result. So we can put down either 1 or 0 here. If you look at the next one, 1, 1, here apparently we have to put down 1, otherwise it will change the digit to be 0. And next digit is still 0. Here we can put down anything. The next digit is 1. Here we don't have choice. We have to make this as 1. This guy, we have to make this as 1 as well. This one is a 1, but the result is 0. Apparently we need a 0 here. And the leftmost digit, we need to make 0 as well. Okay. So by this way, we figure out the what is the numbers should look like. Now we can enumerate all the possible combinations. So we can have the first x to be 0, and the second x to be 0 as well. So this is first x, this is second x. So this number should work. And we can also do 0 for first x, but 1 for second x. That should also work. Or we can make the first x to be 1, second x to be 0. So we got the third choice. The last choice is we can make a number to be this. The last x also be 1. And we find out 4 possible outputs. 4 possible candidates. And if you look at, because we get a character from the standard input, So we need to give a character instead of this binary form. So we have to find out what is the character for these 4 candidates. We can find this is 3, change that to the hex. It will be 3, 4. This is the hex number. Second one is 3, 6, or 3, C. The last one is 3, E. Okay. And we find out the hex number. And the next step is trying to look at the OSC2 table. Let me share the screen to you. The next step is looking at the OSC2 table, find out the character you're gonna use. So we have the 3, 4, 3, 6. If we look at 3, 4, it will be number 4. 3, 6 will be number 6. We have 3B, 3C, that will be smaller than. 3E would be bigger than. So we can try the code. Let's test the results. And let's look at the homework 2. Run the who am I. So the first number is 10. Second one, we either give 4, we will give the return value is 1, or we can give 6, it also gives you return value 1, or if you give smaller than, it will also give you return value 1. The last one is bigger than, and you can still get the return value 1. This will be the 4 characters you can use to make func4 to return 1. Okay, that will be for the func4. Is there any questions? Yeah, John Michael. Yeah, that's right. So if you give 40 or 49 to the standard input, the get char, because it only get 1 character, so it will get the 4 to give that to the func4. So that's a good point. Also, 4049 is also accepted in the homework 2. That's another combination input that can make the func4 to return 1. And yeah, we may use 60, 65, or smaller than number 8. So things like the combination like this can also make the func4 to return 1 as well. Okay, that's good comments. Any other questions? Okay, this is homework 2. And you have the solutions right now. Now let's go back to the practice problem. Last time we are trying to solve this first question. We do a reverse engineering to try to look at what should be the missing, what should be filled at the missing place. Let's quickly go over it. The RDI is having X in it. The ESI is having N in it. And we move the ESI to ECX. So ECX have N as well. We move number 1 to EDX, move number 0 to EAX. We set up the state. Then we jump to L2. L2, we're trying to look at whether RDX equal to 0 or not. That is condition we continue the loop or not. If we look at the for loop, that is the mask that is controlling it. So we know that RDX should be the mask. And from here, we know the condition to continue the loop is mask not equal to 0. And let's look at other stuff. At the line number 3, we move number 1 to EDX. We make the mask to be 1. So we fill out 1 here. And next step, we move 0 to EAX. For the EAX, it has to be result. Otherwise, no other variables. So we have the result to be 0. And then inside of the loop, we're trying to move RDI, which is X, to the R8. So R8 having X, we would do X and RDX, which is mask, put that into R8. And then we do R8 with here R8 with the RAX. So we would have RAX is result, and also put that into RAX. So from here, we know that we should fill out X and mask over here. And then if we look at the line number 10, we shift RDX, which is mask, to the left place by CL. We know CL is the last 8 digits of ECX. We would move by M place. So that's the way we figure out the results for the exercise 1. Yeah, if you have questions, feel free to let me know about this exercise. So this form will pretty likely to appear in our finals. So I would expect you to be familiar about this reverse engineering loop. The next one, this is the exercise also from textbook 3.65. This one is also pretty close to the finals. And let me go through quickly. This will be the pop quiz for you as well. So here we can see we have a nested matrix or nested array. The size of it we define as a macro, which is capital M. We define that to be a certain size. And then we see here is to do a transpose of the matrix. And we find out the assembly code is look like this. Our question is, what should be the size of this nested matrix, or the value of M? What should be it? We have the first one, A and B, to help you to get the final answer of the what should be the good value for M. And now I'll give you 8 minutes. You can look at this question, and this is pop quiz. You can find out in the canvas. I'll show you. And what is the value for M? I'll give you 8 minutes. A question from Tara. A pop quiz today? Yes, there is a pop quiz. Let me show you where you can submit.
I have one.
Sorry?
I have a class literally right after yours, so it's really hard for me to do pop quizzes on Thursdays.
Okay. Yeah. Okay. Yeah. Just send me email. You're good. You don't have to worry if you have some situation like this.
Is this the quiz we're submitting that we're doing right
Yeah, we will submit from Canvas.
Is the problem on Canvas as well, or
it is not on Canvas. It is
okay.
No. So you can go to the assignment. Let me see. There's assignments, and then you would find the pop quiz number 2 right here, and then you can submit your answers from here. And the question is in the slides. So let me switch back to the slides. A question from Paulina. What if we aren't sure how to go about this? Don't worry, you just try, and we just grade by attendance. As long as you submit, and then you will receive full credit. for this exercise, um, the suggestion is try to find out what should be the address for aij, and also what is the address for aji, and um, and try to understand um, this part. You can see here we're trying to add a number to the pointer. Um, this is how much we try to go to the next iteration.
Well, I found the answer, but 15. I don't know. I don't know why.
Wait, are we sending the answers through email or are we doing it through Canvas?
Through Canvas, there is a submission. You can put down your answers in the text box and click submit. We received 11 submissions, and yeah, it's pretty good. I see some of you get the answers. Okay, great. We have about 5 to 6 students. Find out what is correct size for M. A question from Braden. So the pop quiz question is, what is the value for M? Just double checking. Yeah, that's one of the questions. The other two is question A. What is the register holding the pointer? That's the other two questions. But yeah, what is the value of M is the final questions. The first two is helping you to get to the answer. Another question from Ryan. How is 8 being added in the for loop? I'm confused on how it works with the C code. Okay, yeah, that's a good one. And we will talk about the solutions. And after it, hopefully, you would get the idea why there's an 8 involved. Okay, continue to make the summation. Let's conquer these questions together. So for this question, if you the first question is, what should be the registers holding the pointer to aij and aji? We know that for the array, it has to be in memory. So the places in the assembly that is representing this aij and aji should have these parentheses. Let's look at how many we have. We have RDX in the parentheses, RAX in the parentheses. So we can quickly decide either one corresponds to AIJ or AJI. And let's look at the beginning. So first of all, we move RDX in the parentheses to RCX. If we look at the beginning of the loop, we are moving AIJ to a variable t. So quickly we can decide. Let's change the color. RCX should be the t, and RDX should be AIJ. Again, the compiler is a mapping tool. So the first line of the C program usually mapping to the first line of the assembly. So it's a mapping. In this way, we can figure out RDX should be the pointer holding AIJ, and RAX should be the other one, which is AJI. By this way, we figure out what is pointers of it. Any questions so far? Okay, let's continue to do that. The next step, we would make update to RDX and the RAX. We make the update to the pointers. And you can give yourself example. Let's see, we are at the very first iteration. Then we would have AIJ to be a 0, 0. AJI would be A00 as well. This is the first iteration. If we do the second iteration, we find that the AIJ would be A01, right? The AJI would be A10. This is the second iteration. If we look at the pointer, we know the pointer for AIJ is RDX. AIJ is RDX. So we need to update RDX. Previously, RDX points to this A00. In the next iteration, it has to be updated to point to A01. And in this case, you can see RDX plus 8. The reason is from A00 updated to be A01, the address has to be added by the size of one item. The item size is a long, so 8 bytes. So we need to plus 8 bytes to move from A00 to A01. That's why RDX plus 8 right here. A more tricky question is how we update the other pointer. The other pointer is RAX. RAX previously is A00. In the future, it's going to be the A10. And we need to update properly to move the pointer. So this is RAX. This is pointer RAX. And you can see from A00, A10, we need to move the pointers by this much. How to do that calculation? We need to move beyond one subarray. So we have the A00, A01, A02, into A0M minus 1. And the next row is A01. So from at the beginning, RAX is pointing here. So we need to move beyond this row in order to get A01. So how many bytes we need to move beyond? That is the number of elements, which is M. We have M items in between from A00 until A0M minus 1. We have M items. And each item is 8 bytes. So we need to go beyond M times 8 to go to the A0. So A10, sorry, there is A10. In the assembly, we update by 120. So we find out M times 8 should be 120. From here, we know M should be 15. That's how we figure out the size of the nested array. Okay, any questions? Okay, if you are not familiar about this calculation, please look at the textbook and our previous lectures, how we calculate inside of the array or nested arrays. I think that will be helpful to understand this question. And in the finals, our questions would something similar to this one. Okay, so yeah, and also if you haven't submitted your, please do so. Next, let's look at this third question. This one you don't have to submit. I will just explain how to say this question. And for this question, we have two structures: str1 structure, str2 structure, and inside of it we see A and B. And also we have a set value function, which is trying to utilize this structure. And also we know the assembly code for this set value function look like this. The question is, what should be the values for A and B? I will give you 1 minute. You can get you familiar about this question. Okay. So now I will show you how to solve this question. So let's look at the first one. We're trying to refer Q points to T. Q is the struct2, and we look at the T over here. And if we look at the assembly is trying to move the RSI. RSI is a pointer to Q. RSI plus 8 to the place RAX. So RAX is a long variable V1, and the RSI plus 8, this is where the Q, where the T is. So if we look at this struct, we can know that here. Let's draw this struct. First of all, it has a char array, and then has a T, then has SA. We know that for this struct, the pointer is RSI. And here, the number 2 line, we find RSI plus 8 is pointing to the integer T. So from this information, from this line of information, we know that this array should have a size which should be bigger than 4 and smaller than or equal to 8. From you can think about this. If the array size is 4, And then the integer t should have RSI plus 8, plus 4, right? Okay, maybe I need to ask you whether you understand what I'm saying. From this structure, we can figure out the array size should be bigger than 4 and smaller or equal to 8. Do you have any questions? Do you understand it? Or okay, great. Ryan, this question we will answer in the later part. A question from Isaac: why is the low end 4? That's a good question. So somehow this RSI just make it not convenient to understand. How about we just set this RSI to be 0? Just let's assume RSI is 0. And then if we can imagine if the array size is 4, and then it will take 0, 1, 2, 3. And the integer t should start with 4, right? Right now, integer t starts with 8. So that means the array size cannot be 4. It should be more. Otherwise, the t should start with offset 4. Is that clear? Is that? Okay, great. So anything smaller than 4, the integer t would start at the offset 4 instead of 8. So we need to make sure the size of the array is bigger than that. So from here, we can know, actually this is b. The b should be bigger than 4 and smaller or equals to 8. And the next one, if we look at the next one, it is q points to u. It's right here. From here, we can try to continue this struct 2 as a. After it, we should have u. Right now, u is RSI. You can consider RSI to be 0 if you like. 32 would point to the u. And in this case, we can figure out the size of A should be in a range as well. And for the U, you can see the size of U is 8 bytes. The starting address of it should be 24, 32, things like that. So SA should be bigger to beyond 24. Otherwise, the long U would start at 24. The size of it, we can play around. RSI plus 12. So the size of this SA should be bigger than 24. So the A, if let's see SA is making 24, then A is 12. If A is 12, no, A is 6. If A is 6, and SA would stop at 24. And we cannot let that happen, should be bigger than 6. And also A should be smaller than 10. So by this way, the same logic, we can figure out the A should be a number between 6 and 10. And 6 and 10. So you can find out the range for A as well. Do you have any questions about the A? Okay, and using the same kind of idea, you can further look at the next line and try to figure out what should be the range. And finally, you got several ranges. After it, you can try to figure out what should be a good combination, A or B, that satisfying all the equations. And I can tell you the answer is unique. There is just one combination about A and B that would make it happen. Since we running out of time, I would make this to be part of the homework 3. This question, I already go through it. So there's two kinds of idea in order to solve this question. The first idea is when you look at you first the size of the A should make sure it does not go beyond the integer t or the long u. The size of them shouldn't go beyond and across the places of t or u. This is one way to figure out the upper bound. The other way is the size of this array should not be too small, and make the t or u should take the lower address. So this is how to decide the lower bound. After you find out that that's two bounds, you can continue to solve it and try to find a good combination that fits every equations. Okay, this will be this exercise would appear in homework 3. So hopefully we can do it. Yeah, Ryan, if you still have the questions, we can talk about it after class, and that will be our today's content. Thank you for attending. Remember, submit the quiz. Thank you.